Hello everyone, we're going to be doing chapter 6 and 7 review for the final exam, so you'll need your study guides. Feel free to pause at any time during the duration of this so you can copy things down. We'll be doing chapters 9 and 10 review on Tuesday or the next day. Okay, so let's go ahead and get started. So chapter 6 and 7 are looking at rotational motion with planets, also with smaller objects as well. So understand and define the gravitational force. Gravitational force is a force measured in newtons, and we have the universal constant. And the gravitational force depends upon the mass of the two objects, so it's the mass of A times the mass of B, and also the distance is a factor as well. So this F, this is the force of attraction between two objects. So this is relating to this formula. How does distance and mass affect the gravitational force? If we increase the distance by a factor of 3, if you look at this, this is going to be 3 squared. This is also in the denominator. What's going to happen is it's going to decrease your force by a factor of 9. If you have twice the mass, if you increase the mass of either object by a factor of 2, it will directly increase the force by a factor of 2. How does radius and period affect the velocity? Now, this is going to be relating to an object like rotating around your head. It's not a gravitational force, so we're not dealing with the radius or the distance here. So the velocity of an object that's circling is going to be equal to the change in distance over the change in time. And the distance will be the circumference around the circle, which is going to be 2 pi r. And one time around the circle is going to be the period t. So how affecting the radius and the period are going to be affecting the velocity. If you increase the radius and you have the same period, okay, imagine you're circling a ball around your head. It goes around in 1 second. Now we're circling it around the entire school. It's going around in 1 second. What has to happen to that velocity? It has to go very, very fast. So we're increasing the radius, but this is not changing. So we're going to then increase the velocity. If you increase the period, and r is going to be the same, so we're increasing this. So we have a radius. You did this in the Dizzy Lab. You are maintaining the same radius. You're maintaining the same period. You're circling around, but you have same radius, increase in the period, sorry. So you're going to be either slowing this or you're going to be making it faster. In this case, we're going to be increasing the t. We're making it slower by making the time longer. Okay, what's going to happen to your velocity? If you're going to be going slower, your velocity is going to be decreasing. But you can also just look at this mathematically. If this is the same and you are increasing the period or time, you're going to be decreasing that value there. The direction and acceleration for circular motion, and we have the centripetal acceleration is going to be inward. So if we have this formula, F is equal to m times a, Newton's second law, the Fc will also be inward as well. The centripetal force is going to be inward. So if you can imagine the tennis ball on the string, And what is preventing it from flying off? It is the force of tension. Which direction is that force of tension? The force of tension is the centripetal force. It's the inward force preventing the ball from flying off. Where and what the force is on the tennis ball attached to a string, that is going to be your F of T, your force of tension. And again, that's going to be pulling inward. Okay, on to the next page. Understand that centripetal force is not the mythical centrifugal force. Okay, remember, the centripetal force, this is a real force, and it's a real inward force, like the force of tension. There's this mythical centrifugal force, and it's a perceived outward force. And again, it's mythical. So it's a perceived outward force. So if you're riding the spinning ride at the fair or one of the carnivals, whatever the name of that ride is, I can't remember it. We called it the scarf and barf rides. But you're spinning, you are actually traveling in a straight line as the ball would be around a string. And if you were to cut that string, that ball would then fly forward and not outward. So you are on that spinning ride, you are spinning, and you are traveling in a straight path, and the ride is now turning, and you run into the walls as the ride is spinning. So it feels like you are actually flying outward into the walls and being pressed into the walls. But you are not. That's the mythical centrifugal force. There is a real inward force, and that's the centripetal force. Understand how mass and radius and period affect the centripetal force? Well, you have a few formulas. We're going to go back to Newton's. So we have centripetal force is equal to mass times the centripetal acceleration. And there's this formula that's derived from one from class where its centripetal acceleration is v squared over r. And your v is, remember, 2 pi r over t. And this comes out, if you put that into these terms, it would be 4 pi squared r all over t squared. So you can see we have the 2 pi r over t, and all that's going to be squared, which is where we get this value from. So if we plug this into this right here, we get the formula. F, the centripetal force, is going to be equal to the mass times 4 pi squared r all over t squared. So what we're going to do is we're going to change only one variable, the others stay the same. So we're going to change one variable only, and the others are going to stay the same. So if I increase my mass, and my radius stays the same, and my period stays the same, it's going to increase my centripetal force. This again is the Dizzy Lab. If you have more rocks, the radius stays the same, and the time period stays the same, that's going to put a lot more force on your tension scale. So the centripetal force will actually increase. If you increase the radius, okay, what's going to happen is we are having the same period, so we need to go around, but in the same time period. So we have to travel a larger distance with the same time. That's going to equate to a higher velocity. That's going to be a higher centripetal force as well. So it's also a direct relationship. Mass and radius are directly related to the force. It will increase it directly. However, the period, if you increase the period, meaning the time, you're going slower. that's going to decrease your force. And if your mass and radius stay the same, but you're going slower, meaning you have a longer time period, increasing this will inversely have an effect on the force, so it's going to be increasing will be decreasing, increasing and decreasing. There we go. Okay, so these are going to be some calculations. Kepler's square of the period being equal to the cube of the radii. So again, this formula is there for you, but you have to learn how to rearrange this. So you have TA squared over TB squared. It's going to be equal to RA cubed over RB cubed. Okay, so if we're solving for either of these, we have to take the square root of this, or if you're solving for this, you have to take the cubed root of this. Remember to put your unknown on the top rather than on the bottom, because if you put your unknown on the bottom, you have to cross multiply. So key thing is put your unknown on top. When you rearrange these, we can do one of them. We'll take the square root of both sides. So we're going to multiply by TB squared, multiply by TB squared, and then we're going to take, those are going to cancel. We'll then take the square root of both of these as if we're solving for this. This would give us TA is equal to, the square root of this will give me TB times, and then we have the square root of something that is cubed. So this is going to be RA over RB. It's going to be cubed and also square rooted. So this is going to be to the 3/2 exponent. So make sure to try those problems on the homework assignment. If you're solving for RA would equal to, very similar to this, it's going to be equal to RB, but it's going to be times TA over TB, and this is going to be to the 2/3. So you multiply both sides by RB cubed, the RB cubed would cancel, and you'd be left with, we're taking the cube root of both sides, but we're also squaring it. So we're squaring it, but also taking the cube root or the 1/3 root. Make sure that you know how to use exponents on your calculator as well by using parentheses around those. To the power of the parenthesis 2 divided by 3, then you end parenthesis. Centripetal acceleration is, again, AC is equal to V squared over R, and this will be equal to 4 pi squared R over T squared. We discussed that previously. Velocity of an object around a circle. Velocity will be equal to 2 pi R over T, which is why when we put the velocity into here, these values are going to get squared, but we also have an extra R. So one of the R's will get canceled because we have an R squared over an R, which would give us the R up there. And the final formula is going to be force is equal to mass times the acceleration, which is 4 pi squared R all over T squared. So that gets plugged into there. Okay, let's just go for a couple more minutes and we'll just do chapter 9, and we'll end on chapter 9. Understand and define what impulse and momentum are. Impulse is F delta T, and it's equal to momentum, which is mass times velocity, or mass times the change in velocity. So this is not a mathematical one. This is a concept one. What's the impulse? This is the energy to start the motion or to change the motion. The energy to change motion. And mass times velocity is going to be the energy of motion. You have movement, you have energy. So this is the force with a change of time. So if you have a large time, your force would be decreasing. If I remember jumping off a book, I can lock my legs, or I can cushion the blow with some time. So if I increase the time, I decrease the force. And in both cases, it has the same amount of energy. In one case, I have a lower force on my knees. Okay, I decrease the force because I increase the amount of time to cushion them. Or if I decrease the time, my knees are locked, decreasing the time will increase the force. But both of those will be the same energy because I have the same mass, I have the same weight force pushing down. The sum of momentum is the same before and after collisions or explosions. So this is going to be related to the possible problems that you will have as well. So if you have a collision, I'm going to put this formula over here. You have the momentum of the first plus the momentum of the second equaling the final momentum of the first and the final momentum of the second. Okay, so this is going to be also involved with the calculations here. So there's a couple different possibilities. You have the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B being equal to the mass of A times the final velocity of A plus the mass of B times the final velocity of B. Okay, so there's a couple different scenarios that we can have. If one of the velocities is 0, okay, so for example, we have the VA of 1 is going to be equal to 0. If that's the case, then this whole thing will be 0 here, and all the momentum is coming in from the object that's moving. We did this as an example on the floor. I had two carts, one was not moving, the other was moving, and all of the momentum got transferred to the other object. So if they both have velocity at the end, or they have masses, you can calculate what's the final velocity of a certain object. So we know the mass of A, we know the mass of B. We will know the final velocity of A. What's the final velocity of B? And so you have to rearrange for that. Remember that you have your positive direction and your negative direction if they happen to be traveling in opposite directions. You can have the scenario where VA2 does not equal VB2, meaning these are not equal to each other, meaning that they haven't joined, they're not linked, and you can calculate one or the other. So there's a third scenario where you can have your VA2 being equal to your VB2. In this case, this is going to be locked. So the two have locked together, like train cars. One runs into another, and then it is now locked. If that's the case, what happens is, over on the other side, is you have whatever velocities that these are coming in, but for your final momenta, you have the mass of A times V2, because if you remember, these have the same velocity. So the mass of A times whatever the final velocity is, plus the mass of B times the final velocity. And if you're trying to solve for that velocity, you can do V2 MA plus MB. So you have your initial mass, initial velocity, initial mass, initial velocity. One of them could be 0. Both of them could be non-zero. Okay, and we can have a scenario where both of these are not equal, so we have to calculate for one or the other. So it's just an unknown variable to solve for. Trickier one is if they lock together, then the final velocities are going to be the same. And then you can solve for what that final velocity would be. Now, we also have potential for an explosion. An explosion is when you have the two that are pressed against each other or linked to each other, and their initial velocities are going to be 0. So you have a 0 plus 0 equals the final velocity of A plus the final velocity for B. And in this case, one's flying off in one way, one's flying off in the other way, so we have a positive and we have a negative direction. We can have a negative PA2 equaling PB2. Their momenta are going to be equal, but they're going to be traveling in opposite directions. And so then you can put in your values. Negative mass of A times VA2 equals the mass of B times VB2. So that's chapter 6, 7, and 9. Please email me if you have any questions. Let me go ahead and I'm going to zoom in a little bit so you guys can see anything more clearly that you need. I'm going to turn it back to the other page, and I'll zoom in on that too, in case if there's anything on here that you need to see a little bit closer, but I believe you guys should be able to have the ability to also zoom in on your own iPads. Okay, that's it for today. Chapter 10 will be on Tuesday, tomorrow.